This video, we're going to talk about basic compositions of functions. When I say basic compositions, I mean the four basic arithmetic operations of addition, subtraction, multiplication, and division. So, for instance, if we would write f plus g of x, then that would be equal to the function f of x plus the function g of x, and this is just a shorthand notation on the left for what's written on the right. If I would write f minus g of x, that would be equal to f of x minus g of x. And remember that subtraction is addition of the opposite. The opposite is -1 times something. So -1 times g of x, I'll use a multiplication dot because I'm going to use that later. In fact, I'm going to use it right now, that f of x times g of x can be written as f times g, like that. I don't really love this particular notation for function multiplication. I prefer to write fg like that with nothing in between them because there's implied multiplication if there's no symbol in between two letters. So that's f of x times g of x like that. And then our last basic operator that we have is going to be f divided by g of x is going to be f of x divided by g of x. And we need to have the restriction here that g of x cannot be equal to 0 because of what we talked about in finding the domain of a function, that we're not allowed to divide by 0. So let's look at a couple examples of all four of these operators. We're going to start off with linear functions, and then we'll move on to some nonlinear functions in a minute. The first example here is going to be the f of x. It's going to be equal to 4 minus 2x, and g of x is going to be equal to -9x plus 2. And when we add them together, it's going to be equal to 4 plus 2 is 6, and -2 plus a -9 is a -11. Our domain for this function is going to be -∞ to infinity because there were no restrictions in either of the original functions, and there are no restrictions here in the composition of functions. Let's now look at f of x is equal to 4x minus 7, and g of x equal to 8x minus 5. And we're going to find f minus g of x. The reason we're starting off with linear functions for all these first four examples is because linear functions are not going to have any restrictions on them. They're not going to break any of the three rules about the domain. So this is going to be a 4x minus 7 minus 8x minus 5 gives us 4x minus 7 minus 8x plus 5. And that's going to be 4x minus 8x is a -4x, and -7 plus 5 is a -2. So f minus g of x would be -4x minus 2. Again, its domain is going to be all real numbers because there were no restrictions on the equation of this line, no restrictions on the equation of this line, and there's no restrictions on the equation of that line from the composition. third problem here is going to be that f of x is going to be equal to 6x minus 7, and g of x is going to be equal to 7x minus 1. And we're going to find f times g of x. So that's going to be 6x minus 7 times 7x minus 1. We're going to use the FOIL method here, first outside, inside, last, to multiply these binomials together. And 6x times 7x, multiply the first two things together. Now I'm going to multiply the outside things together to get a negative 6x. Now the inside things together to get a negative 49x. And the last things together to get a positive 7. I'm going to combine my like terms there, like so. Clear my domain here on this one again is going to be negative infinity to infinity because there were no restrictions on the original function, and there's no restrictions on my domain of this polynomial down here because there's no division by x, there's no x's inside of an even root, and there's no x's inside of a log. Let's clear my screen here. And let's work on f of x is equal to 4x plus 5, and g of x is equal to 4x minus 1. I want to find f divided by g of x. So that's going to be 4x plus 5 divided by 4x minus 1. Let's remember that my denominator cannot be equal to 0. So I'm going to have to solve that off to the side. X cannot be 1/4. So my answer here for my composition is going to be that it's 4x plus 5 over 4x minus 1, as long as x is not equal to 1/4. Now let's go ahead and let's try doing some compositions with some nonlinear functions. So f of x is equal to 16 minus x squared, and g of x is equal to 4 minus x. So I'm going to add them together first. That's going to be 16 minus x squared plus 4 minus x. And so when I add them, I'm going to add my like terms. So I've got only the negative x squared term for my x squareds. I've only got negative x for my x terms. And I've got 16 plus 4 for my constant terms. I add them together and I get a positive 20. Let's look at f of x being equal to x. Oh, and again, this domain here is going to be negative infinity to infinity because there's no restrictions on this quadratic function for the domain, no restrictions on that linear function for the domain, and there's no restrictions on this quadratic function down here for the domain. Let's look now at f of x is equal to x minus 1, and g of x is equal to 7x squared. When we find f minus g of x, that's x minus 1 minus a 7x squared. So we can write our composition as x minus 1 minus 7x squared. Let's go ahead and rearrange that in descending order of exponents, since that's how we're used to reading things. And my domain of this one is also going to be negative infinity to infinity because there were no restrictions on the linear function, no restrictions on this quadratic function, and no restrictions on this quadratic function when we're done for the domain. Let's clear the canvas and we'll do a couple more examples here. Let's look again at multiplication. F of x is equal to 5x to the third minus 1, and g of x is equal to 2x squared plus 3. When I multiply them together, f times g of x is going to be 5x to the third minus 1 times 2x squared plus 3. And we're going to FOIL again. So f times g of x is going to be 5 times 2 is 10. X cubed times x squared is x to the fifth. 5 times 3 is 15. X to the third. Negative 1 times 2 is negative 2. X to the second. Negative 1 times 3 is negative 3. I don't have any like terms to combine this time. My domain of this polynomial here is still negative infinity to infinity. There were no restrictions on this polynomial, no restrictions on this polynomial, no restrictions on that polynomial. Getting the idea that most of our restrictions are going to come from division unless there's square roots or logs involved. So now let's look at a division problem, and it is also going to have a square root involved. So let's give myself some space for that one. F of x is going to be equal to the square root of x. G of x is going to be equal to 3x minus 2. Now this one had a domain starting off with 0 to infinity, and this one had a domain of negative infinity to infinity. Let's see what happens when I add them together, because I'm going to have a restricted domain so that both of my functions exist, and I'm going to have to restrict when I do the division so that the domain of the composition here for the division is satisfied. So lots of rules going on here. So I've got to have a numerator that exists. So let's look on a number line here. Here's 0. And I need to have x be greater than or equal to 0. And on top of that, I need to make sure that 3x minus 2 is not equal to 0. So 3x is not 2, and x is not 2/3. So 2/3 is somewhere up here. And I've got to put an open circle there to reflect that. So all this stuff that's colored inside there should get rid of. Let's get back to my black pen here. I should not color in on top of that circle. So my domain here is going to be 0 to 2/3, not included, union 2/3 to infinity, not included. That was way different than the other ones because we had a couple of restrictions going on there with the denominator and also in the numerator. So we had to account for both sets of restrictions, and the easiest way for me to show that to you was with this number line technique and then change that into interval notation. I also could write that in set builder notation, x such that x is greater than or equal to 0 and x not equal to 2/3. Let's do a couple more here. F of x is equal to the square root of 8 minus x, and g of x is equal to the square root of x minus 4. we're going to multiply them together here. F times g of x is going to be the square root of 8 minus x times the square root of x minus 4. This domain here was that x needs to be less than or equal to 8. And this domain here is that x has to be greater than or equal to 4. So I'm going to have to take the intersection of those two domains in a second, and I'll get a domain of x having to be between 4 and 8, but we'll figure that out on a number line in just a second here. So when I multiply these things, I'm going to have underneath a single root square root sign 8 minus x and x minus 4 is the square root of, then we're going to FOIL 8x minus 32 minus x squared plus 4x. And so this is going to be negative x squared plus 12x minus 32. Now again, let's look at that number line to make sure that we understand how we get this answer here. That this first function only exists to give me a real number that I can multiply here if x is less than or equal to 8. Let's solve that. If you're unsure what I did, I set it greater than or equal to 0, and I subtracted 8 from both sides, and I divided by -1, which changes the direction of the inequality. And here's 8, and I needed to say that it was going to be to the left over here. It's going to go less than there. And then I'm going to take x minus 4 and set it greater than or equal to 0. And I'm going to solve that. And 4 is somewhere over here. And I need to be greater than or equal to. And both of these things need to be true. So it needs to be the intersection of these two sets of things that they have in common, which is right here. That's their intersection that they have in common, where both things are true at the same time. And that gives me my domain of 4 to 8. That's a closed interval. Let's let f of x be equal to 7x plus 1 over 7x minus 1. And let's let g of x be equal to 2x over 7x minus 1. We know that for both of these that 7x minus 1 can't be 0. So 7x can't be 1 and x can't be 1/7. So that's going to be part of my domain. It might not be all of it. Let's see, we want to subtract. So we've got 7x plus 1 over 7x minus 1 minus 2x over 7x minus 1. So f minus g is going to be 7x plus 1 minus 2x over 7x minus 1. 7 minus 2 is 5. And 7x minus 1, like so. And again, my domain here is going to be that 1/7 is eliminated from the domain. There's an open circle there, so it's everything to the left and everything to the right. So my domain in interval notation is -infinity to 1/7 union 1/7 to infinity. It would be okay to say that my domain was x is not equal to 1/7 as well. That's just as valid. All three of these things express the domain, whether you express it on a number line with a restriction like this, You could put that in set builder notation if you want it to be fancier, or in interval notation. We really like interval notation as we go from pre-calculus into calculus, for reasons that we'll see later when we analyze functions. And last but not least, we have f of x equal to the square root of x plus 11, and g of x equal to 4 divided by x. So the domain of f of x is going to be that x needs to be greater than or equal to negative 11. And the domain of g of x is that x is not equal to 0. Let's take a look now what happens when we take f times g of x, and we take the square root of x plus 11. This is over 1 times 4 over x, and f times g of x is going to be 4 times the square root of x plus 11 over x. And we get both domains have to be fulfilled. So we have negative 11 down here, and we have 0 somewhere up here, and we have a hole there at 0, and we're allowed to be at negative 11, but we have to be greater than that, but we don't fill in that hole at 0 since that's going to violate the restriction of g, and we get a domain that looks like this. And interval notation is the easiest way to do that, but we could also say x greater than or equal to negative 11 and x not equal to 0. All right, that's it for this video. I will come back next time and we'll talk about the difference quotient.